go over how we would select techniques for anti-differentiation. Okay, so the key here is practice, practice, practice. Know what tools you have in your toolbox. Even if you go down the wrong path, you need to know the various paths that you can go down. You need to have that toolbox developed. If you don't have that tool and you need to use it for a particular antiderivative, you're just going to be lost. So you need to have those tools ready. Knowing which one to use takes practice. First, you got to know all the tools, then you got to know which ones to use and where. And the only way that that can be developed is with practicing a lot of antiderivatives. So to start off, I put down a few of these problems here. So we're going to start with this first one. Then we'll go through something like this one here, right? And we'll start to get a sense of what tools, right? And then there's this one right here, right? Which tools is it? And then there's these two right here that we'll go through, and we'll see how it is that each one requires a different tool that can be used. Okay, and to start, this is a beautiful starting one. This is just a basic one where you really want to start off by using the fact that you can just find the antiderivative of this one minus the antiderivative of this one plus the antiderivative of this one plus the antiderivative of this one. And that's written symbolically as the antiderivative of cosine x dx minus the antiderivative of x to the fourth dx. And you're just using that rule where you can just take the antiderivative of each term. And then each one of these opens up to the problem of finding the antiderivative for each one of these, right? So now you got to know how to find the antiderivative for each one of these. The antiderivative of this is just 2 times the antiderivative of cosine x dx. But remember, that's asking the antiderivative of cosine x is the function whose derivative is cosine x. So this is 2 times sine of x, right? Because the derivative of sine x is cosine x. So the antiderivative of cosine x is sine x. Minus. Now here you gotta know basic power rule for antiderivatives, which is just that this becomes x to the 5th over 5, right? The derivative of this will for sure be x to the 4th plus this one here. Now this is a particular case, right? This is really x to the negative 1 dx, right? But we need to know that that power rule where I add 1 does not work for n being negative 1. So the rule I used here, right, the antiderivative of x to the n dx, okay, is always x to the n plus 1 divided by n plus 1 plus c for n not equal to negative 1. And when n is negative 1, right, so the integral of x to the negative 1, or 1 over x dx, is the absolute value of x, ln absolute value of x plus c. And that's what I put here. I'm going to put the constant term at the end, though. So then this is ln absolute value of x plus. And for this one, I'm going to factor out the 5. 1 over 1 plus x squared dx. And this is what I mean when it comes to using our tools. So far we've used this rule, we used this rule. Now there's another thing that's useful to memorize, that the integral from 1 a squared plus x squared dx is arc tan x over a plus C. And now we need to notice that this is of this form, right? This is the general rule. We need to notice that this is of this form here. So I have that A in this case is just 1, right? 1 squared is just 1. So then that means that I can rewrite this, my final answer. I write everything again, the antiderivatives that I found, x to the 5th over 5 plus ln x plus 5 times. Now this whole thing is going to be arc tan x over 1 is just x plus c is my final answer for my antiderivative. And you could sit here and you could take the derivative of all of these terms and you will get back the original one. Okay, and this is illustrative of how I used a few different tools, right? I used this tool, the general power rule. I used the fact that I could break up the original antiderivative into the antiderivative of its pieces, of its terms, right? I used that fact. I used the fact that the antiderivative or integral, the indefinite integral of x to the negative 1 or 1 over x, same thing, is ln absolute value of x. And then I use the fact that I have this, the antiderivative of 1 over a squared plus x squared is going, dx is going to be arc tan x over a plus c. And I could derive that, and you could see how to derive it. You could easily go and find out how. Now, in this case, and this is another one, right? You're just given this antiderivative. I don't know. I'll look at it. Well, what do I have? I have in my pocket always a possible u substitution. And that's exactly what you want to do here. You want to make u in this case. You want to think. You want to make u the one that when you differentiate u, when you do du, is something else in the problem. And in this case, it's sort of clear that the derivative, and this again takes a decent amount of practice, just knowing, right? That u is 1 plus x squared. Because when I differentiate, I'm going to get 2x dx. And then when I solve for dx, I'm going to get 1/2. Right? So 1/2, or 1 over 2x. That's fine. 1 over 2x du. Right? When I divide by the 2x over here. And then when I substitute everything inside here, I'm going to get x stays to start. And then instead of writing 1 plus x squared, I write u. And then instead of writing dx, I write 1 over 2x du. This cancels with this. The 1/2 factors out. 1 over u du. And then you get 1/2. The antiderivative of 1 over u is just ln absolute value of u plus c. Ln absolute value of 1 plus x squared plus c. And then this is now my answer in this case, right? The antiderivative of 1 over u, we use that fact there, that this is just ln absolute value of u. I substitute back for u after it is that I've taken the antiderivative, after I've anti-differentiated, after I've integrated, I plug back in for what u is. And now I'm done with this problem. The trick to begin with is to see that you have that tool of a u substitution and actually utilize it in this case. Because it can be distinguished with something like this very easily. In this case, you actually don't want to do a u substitution. Maybe you think, okay, let's see what happens if you go down the wrong path. Okay, so 1 plus x squared is u. Du is going to be 2x dx. Then dx will be just 1 over 2x again, right? Similar. And now I substitute in. Let's see what happens when I substitute in. I'm going to get the u on the top. And then when I substitute for dx, right, I'm going to get the 2x, 1 over 2x on the bottom. Du, right? du over here, du, right? And then you get this integral 4x squared. And this x didn't cancel. And that's a sign that the u substitution, either your choice for what you made u, or that you don't want to do a u substitution, right? Because you don't have the antiderivative in terms of just u. So in this one, right, I got at the end just 1 over u du as my integrand, right? The 1 over u is my integrand, which is just u's. And then I'm integrating with respect to u. I'm taking the antiderivative with respect to du now. In this case, right, I still have this x squared, this 4x squared at the bottom, which is indicative or indicating, right, that I don't want to do a u substitution, or I made the wrong choice for u. Now, in this case, I actually don't want to do a u substitution. You can try and make u something else, and you'll still run into problems. You could try and make u 2x. That won't help you at all. What you want to do in this case is you want to use a simple fact of algebra, that this can be split up as 1 over 2x plus x squared over 2x dx. And this becomes now the antiderivative of just 1 over 2x plus, this is just x over 2 dx. And now you can break it up, you could say it's the integral of 1 over 2x dx plus the integral or antiderivative of x over 2 dx. And both of these antiderivatives are actually fairly easy. This is a 1/2 or 1/2 that can come out, and it's the antiderivative of 1 over x dx. Another half can come out over here, and this is just the antiderivative of x dx. And again, both of these antiderivatives we should know how to do. The antiderivative of 1 over x is just ln absolute value of x plus the antiderivative of x is x squared over 2. Okay, and then there's the plus c, because now I've taken the antiderivative. So this comes up here. And then, now, the last thing is just to simplify it a little bit. 1/2 ln absolute value of x plus x squared over 4 plus c. And then this is your antiderivative in this case. And you see how, you can go down the wrong path. It's not so easy to just be able to distinguish this integral from this one. Is it literally the same thing but flipped upside down? Pretty much, right? One, you want to do a u substitution, and then the flipped version, you don't need to do a u substitution. You can just use your rules of algebra. Just see that it's just, you could split up the numerator as 1 over 2x plus x squared over 2x. And then you just simplify this right term, right? That's just x over 2 when the x's cancel. And then you take your antiderivative. Now, something like this even further makes it how you got to be able to distinguish between antiderivatives. So one of these is a u substitution, and the other one is completing the square that we went over in the last section. So which one of these are you going to be able to do with a u substitution, and which one is it where you need to complete the square and see it in the form of, right? So we need to be able to see it in the form of 1 over a squared plus x squared, which we said earlier from the other one is just arc tan of x over a plus c. Right, so one of these is going to be, so I get it into this form, and I see it as an arctan problem, and then the other one is going to be just a u substitution. So which one is it going to be? So take your time, think about which one could you actually do using a u substitution, and which one could you do by completing the square to get it in this form. So take your time. Pause it if you like. Think about which one of these is a u substitution and which one of these is a completing the square. So after it is that you've taken some time to figure out which one is which, this one here is the u sub. And this one here is the completing the square. So let's try and do both of these quickly. Let's try and do this one with the u sub. And if you notice, right, why is this a u sub? Because if I make u in this case x squared plus 10x plus 26, right, the derivative of that is going to be 2x plus 10 dx. And then that means that if you can see, if I factor out a 2 here, right, du is 2 times x plus 5 dx. And then this would mean that dx is just 1 over 2 times x plus 5 du. With du on the top, of course. Now, okay, let's substitute this all in and let's see what happens. So I'm going to get the x plus 5, and the trick was to see that that derivative has that factor of x plus 5, because over the whole bottom is u dx. Instead of writing dx, I write 1 over 2 times x plus 5 du. And then this cancels with this, and I get 1 over u du. And now I can actually compute this antiderivative as ln absolute value of u. But what did I forget? I forgot that there's a 2, right? There's a 2 down here. So that 1/2 factors out to the front. 1/2. I was thinking about something completely other than this problem. Don't do that. I'm thinking about how to teach the next one. Always distracted. So here, this here, instead of writing u now, you finish it. You put the plus c here. You finish it by plugging in back for what u is, which is x squared plus 10x plus 26 plus c. And then this is your answer in this case. Okay, now the next one. In this case, what you want to do is you want to complete the square. You want to make it look like this. Okay, that's what's key. You want to make it look like this. The way you do that is you have to complete the square on this inside part. Okay? And it'll allow you to identify an a squared and an x squared or a u squared, right? Sometimes this is written as u. And it'll be easier if I write it as u here, because I'm going to make it u, right? I'm using x already. I don't want to be using x for two different things. So let's call this u squared is u over a, okay? And, then it would be du, okay? So I'm just changing it so it's a little bit better for when we're actually working with this one, which is in terms of x. Okay, how do I do this? You gotta complete the square on that bottom part. So it's x squared plus 10x plus something plus 26 dx. Okay, and that something is what I want to add to this and then subtract from it right away. Okay, so that way I get a perfect square for this quadratic. So what do I add, right? That's the question of how do I complete the square here? Well, this 10, right, is the key number. It's the number next to the x. I take that 10 divided by 2, and then I square it, which is 25. And that's the number that I want to put here. And if I add 25, then I need to subtract 25 in order to make sure that I keep the problem the same, right? Because if I add 25 and subtract 25, I just get the positive 26 to being over here, which doesn't change anything. So then this means that I get 1 over, this here is a perfect square. It factors as x plus 5 squared plus 1 dx. And you could just do the algebra and you could see that this whole thing, x plus 5 squared plus 1 will give you back x squared plus 10x plus 26. Same integrand. Same problem I'm trying to take the antiderivative for. And now this one, if you want to do the u substitution, right, you should see this is the same thing. Okay, this here, right? If you say u is equal to x plus 5, which I always did when I first started doing these problems, the derivative is just dx, right? And that makes things very easy because now you do the substitution. 1 plus u squared now. And instead of writing dx, you just write du because the derivative of x plus 5 is just 1. And the dx is there. So everything substitutes. And now it is very clearly of this form here. And the antiderivative is just going to be arc tan u over 1, because a is 1 in this case, plus c. And then you just substitute back for what u is. Arc tan x plus 5. And I'm not even going to bother putting it over 1, plus c is your answer. And this is how you do it. And you see that there's a wide variety, right? So knowing how to use the tool is already of a level of difficulty, right? Knowing how to complete the square, right, to get this antiderivative. Knowing how to do u substitution is already knowing how to use the u substitution tool. Then, on top of that, it's knowing where to use each tool, which creates an added level of complexity. So knowing how to use all your tools and then where to use the tools is key.